So I want to point out that here for Q in the x direction, this heat rate is occurring over the surface here. It's occurring over this surface. So the area of that surface, because Fourier's law says that the heat rate is proportional to thermal conductivity times the area times the temperature gradient. So the area in this case would be dy times dz for the heat rate in the x direction. Likewise, for the y direction, the area would be dx times dz, and for the z direction, it will be dx times dy. And notice here that I have subscripts on the thermal conductivity for x, y, and z because we haven't made an assumption about thermal conductivity being isotropic. So thermal conductivity can be different in different directions in a material. It can be directionally dependent. So we're making this equation, we're deriving it in its most general form. So the next step, as you may have guessed by now, is to take the Q's and plug them into the partial derivative. And ultimately what that's going to get is that it's going to get us closer to having things in terms of temperature. So we have a box down here. And we're going to take this equation here, the energy in minus energy out. This is our energy balance. And we're going to now substitute in for each component in the appropriate x, y, z direction. So here we have the partial derivative of qx with respect to x times dx. And this equals this relation here, which is hard to see on the board, but you have it in your notes. This is basically saying that it's equal now to the dy times dz, because we have the heat rate occurring over the surface area that's normal to it. And then we pick up this dx here. So we end up now with dy, dz, dx, which is basically the volume that we defined. It's our control volume. So now we have a minus our control volume times this partial derivative, second order partial derivative here that has our thermal conductivity and our partial derivative of with respect to x within it. So we have the same thing for the y and z direction. So you can see that on your paper. I just wanted you to see where that comes from. So now if you take these three relations and you plug them into the energy in minus the energy out balance, then basically now we have a balance in energy in minus energy out in terms of temperature, thermal conductivity, and our spatial dimensions. So now we've dealt with the energy in minus energy out portion of the energy balance. So we're left now with energy generated and energy stored. So let's deal with energy generated first. So this is simple. So we know that Q dot, we talked about this in class before, Q dot is watts per meter cubed. We know that that's what we represent energy generation rate as in this class. So now, to come up with the energy generated term, we just multiply this by the volume. And this is our control volume, dx, dy, dz. And for our energy storage term, we've already been introduced to the fact that the density times the specific heat times the change in temperature with time, because temperature is our sensible energy. And in this problem, we're storing sensible energy. So this heat equation does not consider latent energy. Any type of latent energy would have to be added to it. So this is just a sensible energy heat equation. So we have this term that shows the partial derivative of T with respect to time. And as you would expect, we're multiplying it by the volume, dx times dy times dz. Now if you notice, each of these terms that show up in the heat equation now, energy storage, energy generated, and the terms of energy in minus energy out, all are multiplied by our control volume. So what can we do? Well, we can cancel them out. We can divide by 1. So we get rid of the control volume. So now we made this as an energy balance per meter per meter cubed. Right, so that's what we have. So now we're going to put all this together. Let's put it all together. If we put it all together, our control volume is now canceled out. We're not assuming isotropics. Our thermal conductivity is still inside of this derivative. There's a mistake in your notes, and I'm going to correct that, so you'll actually have a correct version. But I'm going to say this in the video. This actually should not have a power of 2. These should be to the single power, because this is actually just the partial derivative with respect to x of k times the partial derivative of t with respect to x. So there's a 2 in here that shouldn't be in here, and it was, where was it introduced? Well, here it's wrong. So anyway, you should have that in your notes corrected by now. But the most important thing to note here is that now we have this form of the heat equation, and the units now are watts per meter cubed. So now we're balancing heat per control volume. And again, these partial derivatives, this should be a second order partial derivative, is the balance of the energy in minus the energy out. And then here's our heat generation rate and our energy stored. So now we're going to assume isotropic properties. So thermal conductivity does not depend on the direction in the material. So it equals one value for all directions. And then we can simplify to this form. And this is a common form of the heat equation that you'll see. This equation is correct because these are second order partial derivatives of temperature with respect to x, y, and z. So that's a Laplacian. And here we have our heat generation rate divided by k, thermal conductivity. And we have our storage term here. And we have a new friend that shows up, a new term, alpha. And that alpha is thermal diffusivity, which basically is the ratio of thermal conductivity over density times specific heat. And this is the ratio of conducted energy over stored energy. So it kind of gives a sense of how quickly heat energy can move through material. And you can infer that from the units. The units are distance squared over time. So that may make sense to you. And I want to go back to the heat equation that we ended up with and show you the units here are K, so that's temperature, Kelvin, over meter squared. So what we reduced it to was basically an equation that's going to give us temperature over an area. You can look at it like that. So we took an energy equation. We went from watts to watts per meter cubed, and now to Kelvin. Because ultimately what we want to solve for, what we're going to use the heat equation for, is to solve for the temperature distribution inside of the material. So this temperature distribution is a function of x, y, and z, and also time. So that's the heat equation. And we started with Cartesian coordinates. You can do the same thing in cylindrical coordinates, where you start off with a control volume, and instead of having nice, easy to deal with dx, dy, dz, we end up with arc lengths that we have to deal with. So therefore, it makes the equation look a little bit different. And I know you can't see this on the board, but you can see it in your notes. So you end up with 1 over r, some other things that mathematically make it a little bit more complicated. But also, they make the conduction process a little different from conduction in Cartesian coordinates, as we will see when we go to 1D conduction problems, where we consider the difference between conduction in a one-dimensional wall versus a cylindrical one-dimensional system. So we could also do this in spherical coordinates. Spherical coordinates, same thing, just gets a little bit more complicated because of the geometry. And then we have this equation here, which you can see is pretty long, but basically it's taking into account the different angles that you have to consider moving to cylindrical coordinates. All right. So you may have some questions. I'll answer those questions in class on Thursday, but we're going to move on from here. So when you have a partial differential equation,